Ankur sir, should I start?
Yep.
Yeah, okay. So, good morning to one and all present, and a very warm welcome to our distinguished guest and all the participants. Education is a light that shows the right direction to the mankind. India is one of the countries that have the highest number of educational institutions in the world, and consequently the highest number of teachers and faculty members. And increasing internationalization in teaching is strongly supported by the Indian education sector and is considered vital for Indian institutions in developing India's capacity in research and innovation, driving up India's institutional ranking and increasing the quality of teaching and learning. A faculty development program is designed to train and develop professionals in various disciplines so that they can act as resource persons in guiding and motivating young persons to take up right career. The FDPs provide inputs on process and practice of various disciplines such as development, communication, interpersonal skills, creativity, problem solving, training, and inputs on resource and knowledge industries. Participation in such programs would enable faculty members to update their research and pedagogical skills. As learning never ends, Sharda University has organized this online international FDP with the aim of equipping faculty members, research scholars, PG students, and industry professionals with required skills and knowledge. Being an educator is not just about sharing knowledge. It is about making sure that learners accurately assimilate this knowledge and develop learning out of it. This program has facilitated the attendees to get engaged and improve their teaching learning skills to meet the ever changing dynamics in the academic and professional worlds. I'm sure that all of you are learning a lot from the experience of speakers of this FDP who are all renowned persons in their domain. Today, too, we have a very eminent personality with us, and it takes immense pleasure for me to introduce Dr. Daryl Essam to the audience. Dr. Daryl received his BSc degree in computer science from University of New England, Australia in 1990 and his PhD degree from University of New South Wales, Australia in 2000. Since 1994, he has been with the Canberra campus of University of New South Wales, where he is currently a senior lecturer. His research interests include genetic algorithms with a focus on both evolutionary optimization and large-scale problems. He has worked with around 40 HDR students and has led to around 200 publications. He is an expert in the domain of fractal image generation and compression, artificial intelligence, particularly genetic programming, game playing, complex adaptive systems, operations, research, and optimization. With these words, may I now request Dr. Daryl to kindly take over and address the audience. Over to you, sir.
Hey, thank you very much. I'll just start up the share screen.
Yeah, it's visible now, sir. Just, yeah, perfectly visible, sir.
Okay, good. Thank you very much. So my name is Daryl Essam. I'm from UNSW of Canberra. What I'll be talking about today is some research that I've done in conjunction with Rahul Sarkar, who is a strong colleague of mine. And in particular, lots of the more detailed work were done by Tahera Kui, who was a joint PhD student of ours. Both Rahul and I have a strong background in genetic algorithms. Tahera brought a moderate background in neural networks. And so what we're going to work towards in this presentation is essentially some work we did that combined those two fields together. Now, I'm going to start from the very basic elements of both of these fields before joining together to talk about what we had as our ultimate area. So we'll talk about optimization. I'll build up gradually from very simple conventional approaches, which generally rely on mathematical models with very particular constraints. I'll then go on to what are called the population-based algorithms. I'll talk about a few of these a little bit because my main interest is in evolutionary algorithms, and I don't want you to have the impression that I think that is the only way of doing these approaches. So I'll talk about a couple of those so you can see how this family of algorithms work. Then we'll get on to neural networks. And the big thing I want to emphasize as I go through and look at neural networks is just the complexity of designing those neural networks. There are many, many different elements that can be used in neural networks today. And to get performance, you really have to get the best combination of elements. And new research is always introducing new, more complicated elements. And then that just makes the problem of developing a good neural network even more complicated. And then at the very end, what we'll work towards is the combination of these two elements. So to give away the punchline, the idea is rather than having a human trying to design the neural network, we can use our conventional optimization algorithms to design our neural network. In particular, what I'll be talking about is applying that approach to imaging, in particular medical imaging, but it can sort of be used for designing neural networks for really any field at all. And so I'll touch on some of the future research that I've also been involved with, but also that's really the general awareness that I'm trying to impart. The fact that neural networks are very powerful mechanisms, but they're very particular, almost finicky. And so combining population-based optimization with the neural networks can lead to very good outcomes. So when we talk about optimization, this is really the sort of standard problem we have to look at. There's usually some function, we give it a series of inputs, and we're trying to find out where the best values for our inputs or our X, it's really usually a vector of variables, is. So you can see here there are two functions. There's F1. F1 is sort of what conventional optimization would typically be able to solve very, very simply. So we've got a linear function. The two sort of more central lines represent constraints. So we're only interested in the area between those two bounds. And so solving that mathematically is very simple. Essentially, all we've got to do is look at the function and see where it intersects with the constraints. We can, if we've got a point, we can know which direction to go in to try to find the best point. To some extent, it doesn't really matter whether this is a minimization or maximization problem. The same sort of characteristics are there. Then if we look at F2, we can see that it's a much more complicated function. And if you just used a conventional approach where maybe you started at the constraint and then tried to go either up or down towards the outcome, it's more hard to find the actual global optima. We can say there are a few local optima that give us sort of partial solutions, but finding the best one is very difficult. So if we think about conventional optimization, and there is a huge range of problems that can be solved with conventional optimization, the main thing it requires is mathematically nice functions. A lot of earlier sort of mathematics that you may have studied at times is sort of applicable to solving these sorts of problems. Particularly if you have a reasonably smooth fitness function, you can pretty much guarantee for particular functions that The optimal is going to be on a boundary. And if you can do that, these conventional optimization approaches are very, very fast. They also, as long as the function is nice, they can guarantee what they find is the optimal solution to the problem. So that's something when we get to the population-based algorithms, we can't guarantee. But it's certainly a strength of the conventional optimization, that if you have a problem that fulfills its mathematical needs, you can guarantee that you will find the optimal sort of value. So there is an approach where if you're looking at a problem, what happens is the problem is adjusted or smoothed in such a way so it fits the conventional optimization. And then in a sense, you get a guaranteed optimal solution for that problem, but it's not really the problem that you were trying to solve. It's just close to the problem. And maybe that smoothing has gotten rid of or some of the key features that are particularly applicable to what you're doing. So if we have a problem that's more complicated, and what I've got listed there are some of the problems that we can run into. So non-monotonically increasing fitness functions means if you're at a point, you can't always just choose the next better point and use that to sort of hill climb almost towards the best solution. So the previous function I showed to you, which had all those curves in it and different optimal, that's a non-monotonically increasing fitness function. So they're not really suited to the conventional optimization. The problem I also showed you, we had one feasible area between two sort of boundaries. You can have much more complicated feasible spaces where you can have disjoint areas or areas that curve around and aren't sort of uniform in size. You've also got to realize when we're talking about this optimization, the little example I showed you was just a simple two-dimensional sort of image. Really, when we're doing optimization, we're talking about multiple dimensions. So we're talking about multi-dimensional space, which innately adds a great deal of complexity to it. But if we have multi-dimensional space and a reasonably nice function, then conventional optimization is definitely a good solution for it. So the other approach is to use a population base. And by population base, what it means is we keep track of a whole range of different solutions. It could be we just randomly generate the solutions to begin with. Possibly we can have some idea of what good solutions are to start with. And maybe there's a heuristic, there's some rule of thumbs for how you make a good solution. Sometimes you can even do conventional optimization, get some reasonably good solutions, and then put them into the initial population of these population-based optimizers. You can imagine we've somehow got to assess the fitness of all those solutions. So we have to have a fitness function. We can apply it. We can work out which solutions are better than other solutions. And then what all the different population-based algorithms do is they then try to find a new population of solutions. And the big thing that makes them complicated is there's always a tension between, where the current best solution is, you can exploit that solution and presumably find a better solution in that sort of local area, but it might be a local solution. It may not be the global solution. And so there's also got to be some exploration where you try out other possible solutions besides just the original one. Now, the next point is something that you've always got to admit to if you're using these population-based optimizers, is we can't guarantee we're going to find the optimal solution. All we can say is we can try to find a good solution, but it's actually almost a theoretical sort of comparison. If you use a conventional optimizer on a real life problem, you're probably not really solving the real life problem. You're solving an adaptation of that real life problem. And you can find the perfect solution to the adaptation, but it's not the perfect solution to the real world problem. Whereas the population-based optimizers will find you a good solution for the real life problem, and it really will look at the real life problem. So, you know, the trade-offs are not obviously in one direction or another. Now, when we use a population-based optimizer, it can generally work with any sort of fitness function, but maybe it will take longer, and maybe it will have trouble finding good solutions when things are difficult. And what do we mean by difficult? You could have a highly multimodal space, which means there are lots and lots of local optima all over the place. You can imagine if you've got a space with millions of local optima, it can be very hard to find the global optima. But again, we're only trying to claim that we get a good solution. We can have a really unusual search space. We can have lots of disconnected feasible regions, and then you've got to search through not just the solutions that are feasible and whether they're good or not, but sometimes it's hard to actually find any feasible solutions. And we can have large dimensions. That could be lots of variables, or it could be the variable bounds are very, very big. But the larger the search space, the harder it's going to be for a population-based optimizer. But I mean, these are the interesting things to worry about in research. And to some extent, it's an arms race to try to find the better algorithms to deal with these more complicated search spaces. So when we're talking about population-based optimizers, as I said, there's a range of different ones. They all have this tension between exploration and exploitation. So if you're looking at a situation with a complex search space, I would usually tend to look at a genetic algorithm, but there are other alternatives. In some of the research I've done, we've looked at sort of standard test problems, and we've tried to develop algorithms that are better than, you know, the existing algorithms for them. But it's interesting when you look at those test problems, the best population-based algorithms, they're not all the same one. You know, sometimes it'll be an ant-based approach, sometimes it will be a different sort of approach, sometimes it'll be a genetic algorithm. So it's not clear that any of these approaches are innately better than the other ones. Some of them might be more suited to different problems. But what I'd like you to try to see here is just the commonality in them. There might be different characteristics of the different algorithms, but they all, to some extent, have a population of solutions. They all somehow judge those solutions, and then they either decide to keep exploring where it finds the best solutions or to go and do something completely different. So the idea with ant-based optimization is that a solution, we can sort of imagine it as a trail. So this is very simple, which I have here. We just have three variables, x1, x2, x3. We've got particular values for those variables. So we've got here one solution for an ant that's sort of picked x1 as 0, x2 as 1, and x3 as 0. The idea with ant-based optimization is once you've found that path, the idea is you lay pheromone, which is basically an analogy of what happens in the real world, where there are paths, and ants will tend to follow the good paths of other ants. And so the amount of pheromone that gets laid is proportionate to how fit that particular solution is. So you can imagine when you get a new ant to come along, if you want to exploit the situation, it will very much follow the places where the pheromone has been laid before, which is the good solutions. If you want to do more exploration, then it'll have a larger chance to sort of randomly try different possibilities between what's already been found. I've got there as a little tweak, sort of these algorithms, typically over time, the pheromone sort of dissipates. And so, you know, it starts to focus more and more on a particular sort of solution. That's just a general broad overview of the ant-based approach. if you actually looked at this approach, there's a multitude of different alternative versions of all of these different optimization algorithms, where they're just performed in slightly different ways, maybe more appropriately for a particular problem. So it's not as easy as just saying there is just one particular one. Again, there's the question of which particular version do you use. With the ant-based optimization, it's even a bit harder to follow the literature because people develop different versions and name them after different animals, which somehow are supposed to mimic, to some extent, their sort of behavior. So similar to ant-based optimization, you can come across things like bee optimization, and there's a range of other optimizers that all belong to the same family, but have somewhat different characteristics. Then we get on to swarm optimization. So this, we can sort of think of it as a swarm of solutions, again, in two-dimensional space, just to make it sort of simple. So you can imagine we start off with a bunch of initial solutions, and again, we can measure the fitness of those individuals. And to some extent, swarm optimization is sort of inspired a little bit by things like the behavior of birds, the way they sort of flock together in a particular area. So once you've assessed your individuals, each of the individuals is going to move, and there's different elements that can influence it. So to some extent, individuals can be attracted towards the best solution, which again is the exploitation, trying to explore the area where you found the best solution. They're often attracted to the centroid of the solutions, which makes it sort of stay together as a bit of a swarm. So at least it's sort of exploring some sort of common area. There can be momentum, which can be useful if you're sort of traveling in a direction where you've found a solution that's good. Maybe continuing in that direction can find you a better solution. And then there's always some sort of random element. So there's sort of adjustments to where the actual individuals are. And of course, the more random elements are, the more exploration is happening. I mean, with all these algorithms, there's often a bit of an approach where, in fact, the exploration is encouraged to begin with, and then over time, you do more and more exploitation. So you sort of search to begin with, try to find good areas, and then start to exploit in on the particular best areas that you've found. So now we get on to genetic algorithms. So genetic algorithms are very much focused or inspired by what we see in the natural world. So we can talk about things like crossover and mutation. We can even talk about survival of the fittest, that all sort of play into the way genetic algorithms work. So again, we need a bunch of random or maybe seeded individuals to make our initial population. So if we see the first one, which looks like 341162, you can imagine you can have a bunch of variables. Maybe they mean something for the particular problem. They can just be the values of the variables, but maybe they're sort of the amounts you want to carry in different vehicles, or or maybe the numbers encode a particular type that you want to carry. So we can think of them as numbers. The numbers really can represent a huge range of different things. Again, we need to assess the fitness of each solution. So some of them are going to be better than other ones. So in general, one of the major operations in a genetic algorithm is to do crossover. The idea is we have two solutions, and the idea is if we can combine elements of those solutions, we'll get a new solution, and there's at least the possibility that it will be better, especially if we've chosen two individuals that are relatively good. You'd sort of expect their offspring to also potentially be relatively good, or in fact be improved. There's a whole bunch of different ways of doing these operations, and in the next slides I'll talk about these in a bit more detail, because this is the key algorithm that this approach will be working with, as well as the neural networks, obviously. But if we look at the first two individuals, so we've got 341162 and 216342, they're the parents. We've somehow selected them. We'll talk about that, but we'll assume they're relatively better individuals. And so a simple way of doing crossover is to choose some random sort of point in the individual, pick the same point in the other individual, and swap the solutions at that particular point. So in this, we've picked the solution as being just after the first two elements. So you can see with the children, the first individual has got 3, 4 from the first individual and has got 6, 3, 4, 2 from the other one. We can talk about them as parents and children. So we've got the two children that are very much just modifications of the parents. We can then do mutation. So mutation is often we randomly change some of the elements. And then we've got sort of two populations. We've got the old population and we've got the new population. And somehow we have to combine those to get what will be the next generation. What's become more common is probably largely that you throw away the old population and you just use the new population that you've generated, which is presumably a bit better on average than what you had before. But there are different variations with it. And then we go back to step 2 and we just keep doing the same thing again and again and again. And hopefully the crossover will gradually combine the better individuals. That's a little bit the exploitation side of things. And the mutation is really doing the exploration side of things. The difficulty is then developing an algorithm that balances those two things in the best particular way. There are some algorithms where they try to self-adapt the way these operations are being done. So the algorithm can almost change its behavior as it's running, but it is the difficulty. I'd also like to point out with genetic algorithms, another key problem that can happen is because the best individuals are chosen for crossover and they create new individuals that are similar to themselves, sometimes you can end up with a situation where sort of almost all your individuals are almost exactly the same. And that really means the genetic algorithm can't find anything new. And it's sort of a sign that you've got to put more exploration into the algorithm, or you have to have more mutation happening within it. Okay, so when we talked very briefly about how the general structure of a genetic algorithm works, what I want you to see here is just some of the variations that can be done and some of the ways that the algorithm can be tweaked to either emphasize the exploitation or the exploration. Because often that's something that is very problem dependent. You have to find the best values for these things to try to make sure your algorithm finds the best solutions. So when we talk about initialization, it can be random. Sometimes people use a concept which is along the lines of evenly distributing the individuals. If you think of two-dimensional space, it's very easy to imagine the individuals are distributed across that two-dimensional space. And there are similar things for multi-dimension. So you can end up with your individuals not really randomly, and not quite uniformly, but roughly evenly distributed across that multi-dimensional space. You can also, as I talked about before, you can seed some good initial individuals into it. Again, that's something you have to be a little bit careful with, because if you have too many good individuals to begin with, it can attract the whole system towards those good individuals, and you might lose the exploration. It might concentrate too much on exploiting those good individuals you first had, and it misses the exploration of everywhere else. But it is a common approach to inject just a few good initially individuals from somewhere else. They can be heuristics. I've certainly done stuff where we've taken solutions from conventional optimization, put them into the evolutionary algorithm, and then tried to, find better solutions for what the real problem is that you're trying to address. When you do selection, so I said, okay, we select some people to do the crossover with, you somehow have to do that selection, and again, it's got to have a balance. So you want it to generally pick better solutions, but you don't want it to always pick the best solutions. Otherwise, your population collapses down into just being very, very similar far too quickly. So a typical way of doing selection is tournament selection, where you just choose n individuals randomly, and then you select the best. So you can imagine if you choose 10 individuals randomly and select the best, that individual that gets chosen is really going to be in the top 10% on average of your population. If you pick something smaller, like if you pick 2 individuals, you're really just picking like 2 individuals. There's got to be at least a 25% chance that they're both in the bottom half of your distribution, and then you're picking the best one. So it's a much softer form of selection when you've got a smaller value. Lots of algorithms tend to use a tournament selection size of 3, but if you're working with a genetic algorithm, you've got to keep in mind, how are you going to balance this exploration and exploitation? And definitely the size of the tournament size is one of those things. If you find you're converging far too quickly to just a few individuals, you can reduce the size of your tournament and try to give it more exploration. The limit of that is if you have a tournament size of size 2, but if you need to, you can even get even smaller than that. So the second point I have under tournament selection is you can just choose 2 individuals, but don't always pick the best one, add a probability to it. So then, if you set the probability as 55%, you have a very soft selection towards the best individuals. So sometimes in very difficult search spaces where you really need to do exploration, that can be chosen as an option. There are a bunch of other selection techniques. Another common one is roulette wheel, which is sort of, you have your individuals and it's sort of the size they have on the roulette wheel is proportionate to whatever their fitness is. So if you have a really fit individual, it might have a big space. Something smaller has a smaller space. Of course, you do this just with numbers and probability, but so when you spin the wheel, obviously the things that are more fit are going to be chosen more often. So it is an alternative. It's a bit harder to sort of tweak it to how hard or how difficult your search space is. So that's probably one of the reasons why tournament selection is more common. If we get on to crossover, the crossover I told you before was single point. There was just a single point where we did the crossover. You can sort of get more complexity in it by doing multi-point crossover. So instead of having 1 point, you might have 2 points. And so you sort of swap out a middle bit, and you can have multiple points. You can even, at the limit, do what's called uniform crossover. And so when you make a new individual, you randomly choose which of the parents it comes from. So it can have a real mix from the parents. Sometimes when you have a solution, the sort of sub-variables actually work together in some way. And so if you do something like uniform, you run the risk of breaking up any of those patterns. We are sort of talking so far as if the variables don't have any connection to each other. Sometimes you can do what's called permutation problems. So the values might represent things like jobs that you have. So the 1, 5, 2, 3, 4, 6 might say do job 1, then job 5, then job 2, then 3, then 4, then 6. or they can be locations, and you say, go to location 1, then 5, then 2, then 3, then 4, then 6. And so there are no duplicates. Everything just occurs once. So you can imagine if you do a crossover with that, if we did a crossover of just the first 2 elements from each parent, and then the rest comes from the other parent, you can imagine you get duplicates of numbers. So it gets a little bit more complicated. Then you've got to have some sort of repair mechanism that goes through and fixes up the individuals. We've talked about crossovers having 2 parents. That's obviously what we see in nature, but there's no need to keep to that. There are different approaches that use more than 1 parent. 3 is, more common than any other number, but it is certainly a possibility that you can do things with. When we talk about mutation, there's really two elements that can tweak it. So often if you've got an individual, you can say, how many of the variables do you want to mutate? If you mutate a lot of them, you'll be doing lots of exploration. If you mutate just a few of them, it's more exploitation. And then once you've chosen the individuals, you usually shift them somehow. Often people use the normal distribution, but some people use different ones. But you can imagine then the question is, how much do you shift them? If you've got a large standard deviation and you shift them a lot, again, that's encouraging exploration. If it's just a small distribution, then you're doing more exploitation. And there are algorithms that sort of adjust how much mutation is being done as the algorithm runs. So you start focusing more and more on exploitation as the algorithm is running. We talked about permutation. If you've got permutation, you tend not to just shift the variables. It tends to be more that you sort of shuffle them around somehow. So if you are doing a permutation problem, there's almost like a different set of mutations and crossovers that you end up using. But again, thinking about that exploitation thing, the stronger the mutation, the more individuals you change, the bigger the changes are, the more exploration you're doing, which is just one of those things you've got to manage for each problem. Now, I've added 2 extra things in italics because they're not part of the core genetic algorithm that I talked about before, but lots of algorithms have these elements. So elitism is basically just say that when you're creating the new individuals, you don't make it completely new. You might pick the best individual, and that's very common, to just pick the best individual and copy it across to the new individual. Because you can imagine if you make a completely new population, you do have a chance that you lose sort of the best solutions you've found so far. So if you use elitism, you can always keep it, but it does sort of a little bit reduce exploration. So again, you've always got to think about whether it is a good thing to do or not. The other element that can be used to really make a genetic algorithm more powerful is what's called local search. So the idea of local search is it's not done all the time, but every so often, some individuals, it's often not even all of them, sometimes people randomly choose them, or sometimes they just pick a group of the best individuals, or maybe the best one, and you just try to work on that particular individual and make it a bit better. It can just use the standard mutation, sort of like trying out different mutations on it. Sometimes if you've got a particular problem, maybe there's particular heuristics or particular rules of thumbs that you can use to try to improve that particular individual. Sometimes it's done in what's called hill climbing. So you can imagine you've got an individual, you try some mutations. If you find a better individual, you then start with that one and you try to mutate it and try to find a better solution. And so gradually with the local search, hopefully you get a gradually improving individual. Again, it takes time to do this. So you have to sort of balance it between, is it better to just optimize one individual or run the general algorithm? Can also be done just on the very final individual, the best individual that's found by the algorithm. you can always try to refine it using a local search at the very end. Okay, so we've now finished the first half. So we've looked at the population-based optimizers and generally tried to emphasize the idea that they're not going to guarantee you a particular solution, but instead they have to sort of balance this exploration of their search space as well as exploiting the good solutions that they find. So if we're talking about a neural network, the artificial nodes of a neural network are sometimes called perceptrons, and they're modeled on the neural networks that we find in animal brains. Now, if we think of a perceptron, I'll just skip forward a little bit. So here we've got a little neural network in that diagram. Each of those second circles represents a node. If you look at any of those nodes, they always have lines coming into them. They're the inputs that come into them. So each node has a number of inputs. They have some particular strength. Each node also usually has some sort of threshold, and typically when the input starts to exceed that threshold, something will happen, and that will be decided upon by the activation function. So the activation function says, we take in the sum of the inputs, usually you subtract off the threshold, and then you check with the activation function, and that tells you what the output will be. So in biology, it's all done in terms of chemistry, but it's what's called a step function. So each neuron has a certain number of inputs that come in. They give a certain level of product to the neural network. You can essentially add up all the different inputs. Some of the inputs will have different strengths, so they have different weights. And then each neural network will have some sort of threshold. If the sum of all the inputs exceeds the threshold, it becomes active. It usually fires, and then that in turn will go on and potentially fire other neurons as well. In our artificial neural networks, often the activation function uses what's called a sigmoid function. If we have a look at it, you can sort of see that once you reach a certain level, about 0.9 or something above the middle line, you really just get a very strong signal. But the idea with it is you always get a bit of a signal regardless of what the output is. Even if you don't exceed the threshold, you get a little bit of a signal, and that's mainly used for the learning functions. So with the neural network, it has to be trained to adjust to whatever the particular behavior is. And the fact that with the sigmoid function, there's a bit of a signal coming out of all the different nodes helps with training those networks, but it's not really what happens in nature. So you can imagine if you've got one of these nodes at the simplest level, the question is it firing correctly? If it fires correctly, that's okay. If it doesn't fire correctly, you can imagine you've got to change something. And you can either change the input strengths, which means maybe that'll make it more likely or less likely to fire. And you can also change the threshold. Now, really, we have a network. So training is complicated in terms of how you do that for the overall network. And there's also lots of different ways of training those particular networks. If we talk about a simple neural network, and these were really, the most common approach that was used maybe 20 odd years ago. So what we have is if we look at the image that I have there, we're thinking of it in terms of going from left to right. The ones way over on the left-hand side are the input neurons. So they would be coming in from whatever our problem is, saying these are what our inputs are. We've got an intermediate layer here of neurons. So they've got particular inputs coming in. Those inputs will have particular weights. If they get the threshold, they'll then fire according to its output links. And of course, these have weights as well. So that will affect whether the next layer sort of fires, and depending on its thresholds. So what we've got here is our input nodes, some intermediate nodes, and we've got some output nodes. We can talk about a fully connected neural network. What we're looking at there is a fully connected neural network. So each of the layers of the network connects to every other neuron at the next level. It's a bit interesting, even though it's very simple. These networks are very, very powerful, but for their power, they rely on having many, many nodes in that intermediate level, which can be complicated and time-consuming to train. So on one level, this is almost all you need, as long as you could get the right weights for all the different lengths and all the different thresholds. But that is the difficult question. So if we want to train it, you can imagine the question is, we give it a series of inputs. Those links will be active or not active based on the inputs. The intermediate ones may or may not fire, and at the end, the outputs may have some values or well, they may have a value of 0, but they'll always have some sort of value. And then the question is, for those inputs, was that the correct output? If an output node is incorrect, you can imagine you've got to change its threshold and its links. But the problem mightn't be so much with the links and the particular node, it might be at the next layer on. So you can imagine, in terms of fixing this, we'd have to go and change the ones before it, which may in fact have to go back and change the ones before it. That process, and there are lots of different variations of it, is called backpropagation. So it's not the only way to train a neural network, but it's definitely one of the more common ways of training a neural network. In terms of the practical issues of training and eventually testing, because we've got to say whether or not our approaches are worthwhile or not, it's good practice to divide into a training and a test set, so we can train our neural network as much as we want on our training set, and then eventually test that on the test set to find out how good it really is. How much does it generalize? That's particularly an issue with neural networks, because even those simple networks, you don't actually have to have too many intermediate nodes, and it can do what's called overtraining. It can really lock in and just learn the particular test sets or training set you're giving to it, and maybe it won't really generalize very much. Now, with the training, typically the idea is you present all the different input sources you have to the training, and you don't adjust the neural network to completely be correct for each training set. It's more, you train it a little bit in the correct direction. And so you can give it all the different images. It gradually changes and adapts to those particular images. You can even do it multiple times as you run through the training set, and it gradually learns and adapts to that particular training set you have. Now, often there's a problem with neural networks in that you need lots of training data. There is a technique called data augmentation, which is where you take the training data you have and sort of modify it and change it so that you can get even more training data. So when we're talking about images, it's relatively easy to augment your training data. You can do things like you can flip images around, you can rotate them, you can shift them, you can scale them and zoom them in and out. And so you can make a sort of a much larger training set than what you had originally. But you have to keep in mind this principle that even with lots of training sets, you always run this risk of overtraining. So the next point I've got is some ways of adapting or dealing with this sort of issue. So with a neural network, it can be very good at finding things. So if you are looking at images of potentially cancerous scans, it's always possible that a neural network will discover that if you have a scan and maybe for this particular scan, they've left a date on when the scan occurred, maybe it will work out that there's only one scan that was done on the 3rd of July in 2011, and that was a cancerous image. So it will learn that thing rather than the sort of things you think might be applicable for working out in general whether or not an image represents a cancerous sort of image or a non-cancerous one. So that's what the validation test set is for. So the idea is, as you train your image, you should see the training sort of fitness improve over time as it gets better and better. The idea of the validation is you then also train, well, you don't train it, but you test the network on this separate validation set. And you should see the validation set improves, or the neural network's performance on the validation set improves at the same time as it improves with the training set. But if you notice a situation where the training set improves, but the validation set doesn't, that's a very strong sign that overfitting is occurring. And it really means you need to sort of like unwind your neural network to the previous stage and say, that's the neural network we'll use. There's another idea which is called dropouts. Again, it's a technique to try to make it more difficult for a neural network to overtrain. The idea is just that when you're running it, you decide that randomly that some of the intermediate nodes will just be ignored. You'll run it as if they're not there. So if some of the time some of the nodes are there and some of them aren't, it sort of forces the system to act a little bit more general. So that's another approach that can be used for this overfitting issue. Now, this is really the heart of modern neural networks. So when people commonly use neural networks today, they use what's called a deep neural network. And the idea is you have your inputs that come in. So the inputs that come in at the left, we then go through to different layers of networks. And these layers have often got a particular structure that somehow relates to the particular problem. In imaging, which is what I've been looking at in more detail, typically these might say reduce the resolution of an image to try to focus on more general elements. But for many different situations with a neural network, there'll be different layers sort of focusing on different elements. I mean, to some extent, each layer, we can think of it as you get a series of inputs in and you give a series of outputs. It's really a type of a function. So we really get the inputs and then we transform it through a series of functions until we get to our final sort of result. I mean, the principle of divide and conquer is a very common approach for solving a problem. And to some extent, the deep neural network is a way of trying to work on this divide and conquer, of looking at particular sub-issues with each layer as we get towards the final sort of image. Now, there's no restrictions that they all have to be the same size or have the same characteristic. Each layer can have different sizes. The number of inputs and outputs at each level can be different. So there can be quite a variety of them, all being tuned in to different sort of elements. Now we're getting much closer to the system I'm really going to be focusing on. So this is what's called a fully convolutional network. So what the fully conventional network does is it takes the input image in and then goes through a series of blocks where it changes. And typically on the input side, on the left-hand side, what's happening is the resolution is being reduced at each stage. Now, when you reduce a series of pixels, there's really a number of ways of doing it. You can sort of like pull them all together. You can take like 4 pixels, pull them all together into sort of like their average value. This uses its max value, so the maximum of the values it's pulling. So as it goes down through the different stages, it's reducing the resolution, presumably trying to focus on what's more important for the problem that is at hand. You can see it goes down to the very bottom, that's called the bridging layer, and then it starts going back up again. So at each level, it's then got to expand the image back out to its full size. So essentially, there's the opposite operation of the max pooling as it increases the size. So the idea is you go back upwards, there's sort of like a right-hand block that will correspond in size to the left-hand block on the same level. There's also the crop and copy, which is basically saying that the output from the matching level on the left-hand side goes across and is given as an input on the right-hand side. So it not only has the base image, but it has whatever was determined as being appropriate over on the left-hand side. So then as it goes up and expands out, it can expand on what it has, but it also has that extra information coming across from the left-hand side. These are fully convolutional networks have been very successful in terms of image identification and also what's called image segmentation. So particularly in what we've been looking at with medical imaging, if you have a slide, you may know there is a cancerous tumor on it, but the question is, where is that cancerous tumor? Whereabouts are its edges? That's what image segmentation is referring to. So if we're doing a fully conventional network, there are all sorts of design issues that have to be made. You have to decide how many blocks there are going to be, what's going to be the level of compression of the different images as you go through the different layers. And then there's all the general neural network questions. How many sub-layers are going to be in each of these blocks? How many neural networks are they going to be? What are the activation functions going to be? How are you even going to learn the different things you need to learn at each of these levels? So it's more a framework. There's still lots of details that have to be filled in to get the fully conventional algorithm for your particular problem. There are many different approaches that have been used to optimize these deep networks. I'm not going to try to go into all of the different ones, but because we've used the attention mechanism to get relatively good results, I just wanted to give at least a bit of a flavor of what the attention mechanism means. So you can imagine if you have an image, particularly, you know, if we're thinking of a cancerous image, there are going to be some areas that are particularly important to your particular problem. And the idea of an attention mechanism is it's going to choose particular inputs based on the importance. So if there's a heuristic we can use that will tell us which bits of the image are more likely to be cancerous, we can focus on those particular bits. A slightly different approach to using a heuristic is actually to use a neural network. So having a neural network which assigns weights to try to choose the right sections of each image. There is a range of different attention mechanisms. So again, deciding which is the correct attention mechanism and implementing it in your particular problem is just another bit that sort of expands the search space of what to look at to try to find the best particular solution for your particular problem. So this is really the ultimate point of what this presentation has been getting to. So whatever data sets you have, finding a good deep neural network for your problem, along with all its parameters, is very hard. Where I am, one of my jobs is actually reviewing and coordinating our PhD students at my university. So I see a range of different people's research, besides just the sort of niche area that I look at. And there are many fields where it seems like where I am, it's an engineering school. They might be trying to optimize the edge of a wing for an aircraft, and almost an entire PhD, which is a 3.5-year process, will be spent trying to find the right neural network for that particular problem. It really is a very difficult search space that can be very time consuming. Frustratingly, even if you find a good structure for one particular problem, you just have to change the problem slightly. So I'll show you some results soon, but you can have an algorithm that's good for, say, prostate cancer, but it isn't so good at liver cancer and needs some other sort of structure for it. So the giveaway I said at the very beginning is the work I'm going to show you has basically used a genetic algorithm to make all these choices, to choose what the layers of the convolutional network are going to be, what the attention network is going to be, what the size of the different layers are. And rather than having someone essentially trying all these different possibilities themselves, I mean, people do have the advantage in that they can sort of try things and go, well, that seemed to be good, so I'll keep that, but I'll try to change this in a way to be optimal. I mean, if you have a machine learning algorithm, it probably won't choose, if you only get 50 choices, it probably won't choose a good 50 just as good as the human chooses 50. But with a neural network, you can try hundreds or thousands of possibilities. And really with all these approaches, it's more like a guided randomness. So we find the things that are good, we can do changes to them and gradually try to get a better and better solution. So really what I'm going to show you is just an example of using a neural network to optimize finding deep neural networks for medical imaging. But it's an approach that can be used for many, many, many other deep neural network issues. So this is really the first work that we ever did. So on the right, you can see the hyperparameters. So they're the parameters that our neural network had to decide. So it had to decide things like the number of layers, what size the filters were. We talked about dropout. How much dropout did you want? Did you want to use? Whether pooling was supposed to be average or maximum, and a few other sort of connections. The shortcut and long connections refer to the shortcut are sub blocks, and the long blocks are the across the convolutional network connectors. The batch normalization, really, because we have a bunch of different blocks, we can say which blocks are being active and which aren't. It sort of means, even though in our, sometimes we call it the genotype, in our genes we'll have code or choices for 7 blocks, that batch normalization will be able to say, oh, actually you only use these 3 blocks. So it sort of means we have a variable size. We can have up to 7 actual blocks, but we don't really need to use all of them. With the U network, because the right-hand side is the same as the left-hand side, at least in terms of their size, we don't actually need to keep track of what we do for the right-hand size. So if it works out there are 3 blocks, that'll be 3 blocks on the left and 3 blocks on the right. You can see the optimizer. So I said there are multiple ways of learning with the algorithm. I mean, if you're hard coding your neural network, you have to make these choices and you have to decide whether to change them or something else. Whereas with us, it's just another parameter. So we can choose the optimizer. I said when you see a network, you can, or when you see an input, you can choose how much you modify the network to adjust to that particular image, because we don't want it to completely change to fit that particular image. So we can give different values of the learning rate. So that basically, if it picks 0.001, it's only going to do slight changes as it gets to images. Otherwise, it'll do much stronger cases or much stronger changes. And so this is the sort of thing we were aiming at with all the different comparisons. So what's interesting is to look at things like the UNet algorithm. And you can see that its behavior, I mean, the behaviors are always going to change based on how difficult it is or less difficult for the different sorts of images. Promise 12 is prostate cancer, and there's different sort of subgroups for it. Sliver is liver. The other ones are different sort of elements. But you can imagine what they've got is they have a particular structure that they've optimized for a particular code, but maybe it's not the best sort of code to have for other sort of images. Whereas with our system, what we can do is, you know, it essentially adapts and finds the best neural network for each of those particular problems. So it sort of makes sense. It finds a better network for each of those problems. But, you know, we haven't had to lock a PhD student in an office for months and months to do this. We've just let the algorithm run and work out what the optimal value is for those particular sort of elements. That's for two-dimensional segmentation. You can see with the first block, they're sort of conventional fixed approaches. The second and third bottom approaches are actually alternate evolutionary neural networks. I mean, it's one of the things with computers getting more and more powerful, you can sort of do more complicated training or run your systems longer or have more complicated potential networks just as computing becomes more powerful. I mean, the key sort of differences between our algorithm and the previous ones is just the range of things that the genetic algorithm could optimize in terms of trying to find the best solution. We also looked at 3D, three-dimensional images, which are often the same sort of data sets, but the data sets will have sort of two subforms inside them. They have a two-dimensional image and a three-dimensional image. Without an attention mechanism, our results were okay, but they weren't overwhelmingly good, I guess. So when we're looking at three-dimensional images, we have more genes, we have a few more variations. I mean, in terms of time, we're talking about 2 years in time, really, between when the first system was developed and then this system was developed. So we had learnt more in terms of what sort of things we did want to allow in terms of variation. Notice the attention mechanism or the attention module, which is just the second bottom of the convolutional block over here. Its options are really 1 to 6. So these are 6 different types of attention mechanism. So the big thing that let us perform well for the three-dimensional images was really to say, okay, what we're going to do is we'll let the algorithm have an attention sort of mechanism, but it will also have to choose which attention mechanism it has. And so it's got different sort of elements for different sort of settings based on what's appropriate for those sets. I haven't gone into it at all, but in the papers that we've done for this research, we've actually done a reasonable amount of study in terms of trying to work out what the patterns are with the different databases. So we can see with our solutions that particular formats were more or less used across all of the images, and in fact, you know, which ones tended to be used for which ones and which ones didn't, which is an interesting sort of sidelight in terms of showing the effectiveness of different options. So once again, we sort of managed to beat the existing techniques. Again, you know, the people who developed the sort of previous elements, I mean, they're very clever people who develop their particular options with neural networks, but they just have this limitation that whatever structure they find that will be good for one set of images is usually not optimal for other sets of images. I mean, it's also, even where they've focused on a particular set of images, just the fact that our genetic algorithms can go through and look at a huge range of different possible networks, we can usually beat them on the individual one that they did look at. It's also an interesting sort of point in that, you know, to some extent, as we were developing our work, we would often go, oh, we're having trouble beating a particular system. What does it have that we don't have? And that led us to things like the attention mechanism. And then we would realize that different algorithms were using different versions of that approach. And of course, using the genetic algorithm, we can always just encode that as part of the genotype, and it can go and evolve its particular solution. It's probably also worth pointing out the genetic algorithm we've used for this really isn't a very complicated genetic algorithm. When we started, we thought we'd have to spend a lot of work trying to work out the best combinations of operators and different parameters for our genetic algorithm to work well. And there has been a little bit of that. We've had to work out how big our populations should be and what our force for mutation and crossover should be. But we haven't really introduced a lot of unusual features in the genetic algorithm. In some ways, it's a relatively standard genetic algorithm that is just optimizing what is a very difficult search space, which so largely so far has been done by humans, almost by a series of trial and error, trying to find the best sort of option. So if we wrap all of this up, so when we talk about neuro evolution, we're talking about an approach that we can use for all sorts of data sets to try to give us advantages rather than having to spend our time manually working out what the best settings are for our neural network. We're sort of continuing to use this for other approaches. I haven't showed the results for it because it's still not very much into the submission sort of process, but we've looked at a bunch of different imaging problems and really just thrown our existing algorithm at them And we haven't got the best sort of solution for maybe about 3 of the 10 different data sets we have. But if you compare any of the existing ones, we're sort of beating all of them on a one-to-one sort of basis. Because again, it just has that ability to adapt to whatever the problem is going to be. We've also got some work where we're doing some stuff with the Australian Bureau of Statistics in terms of they like to do predictions for various factors in the economy. One of them is the electricity demand of the economy. And so we're trying to develop a neural network that will outperform the existing techniques. And again, we're going to use a genetic algorithm to tune that neural network rather than spending far too much time trying to find the best parameters and operations of the neural network. I mean, we also have this, I think I did cast on it a little bit earlier, but we do have this ability to, as we see new mechanisms appear in the literature for neural networks, we can just incorporate them into our genotype. And so we can very quickly adapt to new directions in the research literature. Anyway, so that's the end of my presentation. I hope it's been interesting, but if anyone has any questions, I'm happy to take them.
Thank you very much, sir. It was definitely very interesting. And I can see some questions in the chat window. So let me read it for you, sir. The first question is, can we use bio-inspired optimization for any type of classification and feature selection?
Well, you can. I mean, the big thing is, as long as you've got a fitness function, you can use it. It does take a little bit of experimentation with evolutionary approaches to really get a feel for how they're performing. And so getting that balance between exploration and exploitation. But yes, I think you could.
Okay, so the next question is, how can we deal with imbalanced data set in deep learning?
Well, if you have an imbalanced data set, that seems a little bit outside of the scope of what I've looked at, but I would think you could use data augmentation to some extent, where you could augment the less common elements to scale up their performance. So if you did have some distribution of data inputs you wanted to consider, I think you could get that as long as you could do enough augmentation.
So the next question is in continuation to the previous question, sir. And as you said that we can augment the data, so what are the different text data augmentation techniques?
Well, text to data, again, I think I actually did some work on working out what's called whether comments are positive or negative in Urdu/Hindu recently. And so we had a lot of text in that. But I don't think we used augmentation in it. I'm sorry, I don't really know what you could do with text. I mean, if you can work out substitutions to words in the text in terms of, you know, there are words that mean the same thing or phrases that are the same thing, and then you have code to automatically do those changes, that would, I think, give you some assistance that way. But, you know, often words, you can't necessarily swap them one by one. They might be a little bit odd. So that may not be perfect, but it still might be a good enough solution.
Okay, thank you, sir. And the next question is, how autoencoders can support dimensionality reduction?
What encoders can? Well, if we're talking about an encoder as being a neural network always has a series of inputs and a series of outputs. To some extent, if you have less outputs than inputs, you will be having a reduction in the dimensionality. Other than that, I think it's very problem specific. So if you have imaging, it's relatively simple to downsample your pixels, deciding how you're going to pull the different pixels, you do that. For other problems, on one level, it can be more complicated to find exactly how to do it, but by adjusting the number of inputs and outputs, you can get elements of that approach.
Yeah, thank you very much, sir. Rest, I can see my chat window is full of appreciation messages now. And yes, we have received another question that can we use GANs for data augmentation or images?
I've seen GAMs used for image reconstruction. I mean, that's interesting because, I mean, if you're using GAMs for data reconstruction, it probably won't reconstruct things exactly as they were originally. So if you were using GAMs and you had images, you were blocking out particular bits of them and asking GAMs to reconstruct them, you would get different elements, which you could use. I've just found with imaging, just being able to shift and zoom and rotate and crop standard sort of imaging things has given us a big enough range. But I think that could be an interesting approach that could do another increase in the amount of data you have.
Thank you so much, sir. Thank you so much for so patiently answering the questions of the participants. And if there are any other questions, I think the participants can write directly to the speaker and so that he can answer those queries in detail. And as I can see that we have also been joined by our Dean, Professor Dr. Parmanand, and HOD, Computer Science and Engineering Department, Dr. Nitin Rakesh. A very, very warm welcome to both of you, sir. And may I now request Dr. Ankur Chaudhary to kindly present the summary report of the FDP.
A very good afternoon to one and all present here. Respected distinguished speaker, Professor Daryl, and the participants who have devoted time to grace this faculty development program with their online presence. The RACSAD 2021 is now drawing to close. I, Ankur Chaudhary, along with my fellow organizers, Dr. Arun Prakash Agarwal, Dr. Gaurav Raj, Dr. Vishal Jain, and Mr. Abhishek Singh Verma, take this opportunity to extend our sincere gratitude and appreciation to all of you for your valuable participation in making this event a grand success. RACSAD initiative was taken last year to nurture the talent and promote innovation as per the vision of our respected Chancellor Sir, dynamic Pro Chancellor Sir, and Vice Chancellor Sir. Without enormous support and guidance of our Dean Professor Dr. Parmanand and Head of the Department Professor Dr. Nitin Rakesh, we would have not been able to host this international event, which is third in series. We hope that past 6 days have been productive enough, and we are sure that you must have gained tremendous knowledge from the different sessions organized during the FDP. Let me tell you that 278 participants, around 140 unique institutions from countries like USA, Canada, Malaysia, Oman, UAE, Serbia, Saudi Africa, India, Nigeria, Nepal, and Uzbekistan participated sincerely in this FDP. We received participation from top Indian universities like IIT Delhi, Yadavpur University, JNU, Jamia Millia Islamia, and IIT Dhanbad, to name a few. We also received participation from companies like Amazon, Best Buy Canada, Home Screen Network, Will Blockchain Development, including Ministry of Electronics and Information Technology, Government of India. During this FDP, we have witnessed 13 eminent industry speakers, scientists, and researchers from the University of Repute, including University of South Wales, Australia, from both Sydney campus as well as Canberra campus, Bournemouth University, UK, Monash University, Australia, RMIT University, Australia, IISc Bangalore, India, and Distributed System Group, Australia, and the company from E&Y, Canada, to name a few. Our heartful gratitude to all of them for sharing their expertise with us over past 6 days. Now, may I request Dean sir to say a few words.
Yeah, good afternoon, all of you. And I'd like to thank you, all the participants, organizers, our management, head, computer science engineering, Dr. Ankur, Dr. Arun, Dr. Gauraraj, Dr. Vishal, and other colleagues of computer science engineering. This is the final day of our 6-day FDP program. That is recent advances in computer science and allied domain. In sequence, this is the second FDP program from the Department of Computer Science Engineering, and the same organizing team has organized. I'm happy to say that the experts were all from all over the world, and today's speaker, Professor Daryl, has presented very good keynote. Apart from him, many experts of their domain presented their own expertise. They talked about their area and enlighten all the participants. The participants are also from many places, many cities, many countries, as told by Dr. Ankur. Of course, it was a tough time because in parallel there were two conferences, two FDP programs were running. And it was well managed by the organizing team. Let me again congratulate all the organizing members and Department of Computer Science, making this event a grand success. Thank you and wish you all the best, and hope all the participants as well as all the experts will join again whenever we have such kind of grand FDP or workshop inside the university. Thank you. And over to
Thank you very much, sir.
Arun.
Thank you. Thank you very much, sir, for your kind words. And let me thank you once again, because it would have not been possible without your enormous support, sir.
Thank you.
You always give us a free hand, sir. That is very, very thankful, sir. We are very thankful to you.
Now, may I request HOD sir to say a few words, please? Nathan sir.
Thank you. So thanks, Dr. Ankur. A wonderful event actually is coming to a conclusion. But I would like to say that this is not just a concluding of this event or just the end of the learning event. It is just the start of a new possibilities and the questions which are being opened during the esteem talks. This event will also open various opportunities for all the participants to have a fruitful collaboration with all the wonderful speakers, all the 14 speakers we are having in this FDP. I thanks all the esteemed speakers to devote their time for this FDP to make it a grand success. The success is not possible if the participants from various and distinct states have been the part of this event. So I'm thankful to all the participants to attend it with full sincerity and attending with some sense of collaborative outcomes also. So identify where this learning can open the possibilities to link with the speakers of various events as per your requirement or your needs and contact them for any further questions or queries for your future research. It is wonderfully organized by our team of Professor Ankur, Professor Arun, Professor Vishal, Professor Gaurav, and Professor Abhishek. From the day one till the end of the event, there is no glitch, neither technically nor in sense of any execution problem had been faced by either the participants or the speakers. Though we know that there is a parallel FDP going on in university on a higher note and the involvement of internal faculty members have been engaged, but still this event has not been affected with because it has already been having the potential to post the participants with the sessions which have been engaged with. So thank you one and all. I am very thankful to the base creator of this event, our respected Dean sir. Thank you sir for giving us energy and motivation to organize such wonderful events. Thank you.
Thank you, Nitin sir. Thank you so much for your kind words. And let me tell you from this platform only that we have received various internship opportunities and collaboration opportunities from many of our speakers. They are open for collaboration. So we will further utilize this platform to materialize those collaborations in several forms, like in joint research paper writings and internship offers to our graduate and undergraduate students.
That's very good. I think we can actually, if possible, pen down all these things as a part of the immediate outcome of this FDP. So it is great to have this immediate outcome if it can be analyzed in form of some keywords. Thank you, Dr. Arun.
Thank you. Now, may I request Dr. Kamal Karnatak to kindly share his experience about this FDP and say a few words if you want to share his experience.
Yeah, so it was a wonderful experience. Throughout 5-6 days, I have learned a lot. So I come from an industry. For me, it was a new thing. I have done my PhD from IIT Delhi, and through that, I am attached to the academics as a subject. But since we work in the industry, we deal with the practical version of the thing. We may not get those kind of chances there where these kind of things are there and we can learn by theory also. So it has given me a good chance of learning through that. I have noted a lot of things. So as Nitin says, it is not the end of this FDP. Actually, it is a start. For me, actually, I have noted down many things, many papers which I need to read, which I need to study in next 10-15 days. So I would like to thank all the organizers and Sharda University for this wonderful initiative. From the collaboration point of view, I am also part of a organization called CIOs of India. I am a president of CIOs of India. So it's an industry body of last 25 years. It was started in 1996, a non-profit organization. If you see that there can be a collaboration opportunity with your university or with any of the student or participant, I am ready to open for that, so we can connect offline after this event, and we can also facilitate that kind of collaboration from industry point of view. Thank you all.
So nice of you, sir. So nice of you for your words of appreciation. May I request now Dr. Somi Ghosh, because I can see that she is a very patient and very sincere listener, very sincere participant of this FDP, if she wants to share her experience with us. Dr. Somi Ghosh, are you there? Can you hear me? No, I think she is busy somewhere. Any other participants, if he or she wants to share his or her experience, or if you want to suggest for any
A very
improvement.
good afternoon, sir.
Yeah, good afternoon, Somi ji. Would you like to share your experience, Dr. Somi?
Am I audible, sir?
Yeah, you are audible. You are audible, ma'am.
A very good afternoon, sir.
Good afternoon. Good afternoon.
Sir, it's really an awesome opportunity that you give me to join all these FDPs of Sharda University. I have joined all the last 3 university FDPs, and throughout all the FDPs, excellent speakers were there. Last year also, there was a keynote speak by from technical field of as well as today also there was a lot of good speakers were there, especially the deep learning session was the excellent one. I can't express my words in that. It was really awesome one, and for that I also requested you for the giving us the recordings of that session. So it was really awesome. Every time I say that, every time, sir, you always bring excellent speakers from all over the world for make us more knowledgeable in our field, and it's really helped us, sir. Thanks a lot, sir.
And thank you, Dr. Somi. Anybody else who wants to share or who wants to give their valuable feedback? We are open for suggestions. I think I can, Dr. Hamnabad. Yes, sir. You can. I think you can unmute yourself now.
Sir, very good afternoon. Sir, whether I am audible to you?
Yeah, you are audible, sir. You can switch on your video also if you are comfortable.
Maybe may not be that clear, but however, so let me just say a few words. Video may not be that clear.
It's okay,
Sir, it
sir.
is clear,
It's okay.
sir.
Okay, sir. Sir, thanks a lot. So organizing this FTP. This is my second FTP in Sharda University. First one I have attended. This is third one I have attended. Sir, thank you very much for inviting such an eminent speakers. So which made, I think, all participants, especially to me, I learned a lot. So Sharda University, and then all your teams are so keeping the time schedule and the kind of events you are organizing. Okay, so thank you very much, sir. So thank you very much for giving me this opportunity to participate in this FT. Thank you, sir. Thank you.
Thank you so much, sir, for your words of appreciation. I think Dr. Amandeep is with us now. Dr. Amandeep.
Yeah, good afternoon, sir. Am I audible clearly?
Yeah, you
Yes,
are
sir.
audible, sir. You are audible.
Thanks a lot, sir. I just want to express my sincere gratitude to get opportunity for attending this wonderful and very informative faculty development program. Actually, I have also attended many of FDPs and webinars already organized by Dr. Vishal, sir, since last year when he was in Delhi University. So it's very good opportunity for me to attend another one FTP organized by Vishal sir and a whole team. So one of my suggestions, sir, kindly organize another FDP or STC over the IIoT, that is Industrial Internet of Things. It's a security threats and how to mitigate the security flaws in there. So if
Yeah,
possible, kindly organize in short time, sir.
we will definitely consider your request, sir, and we will come out with an FDP on this.
I
Yeah,
would
please,
like
sir.
to just put up. Dr. Amandeep, recently, just before this FDP, we have organized an event on cyber security in collaboration with Microsoft. And that FDP is also belonging for 7 days. But we were next time give a proper circulation to you properly for this event on industrial IoT also. We were having few sessions on IoT for the security concern in that FDP, but in next time we are already putting up for a wider circulation also.
Right, sir. Right. Thank you so much,
Thank
sir.
you for your
Thanks a lot.
suggestion. Thank you.
I think
Thanks
Dr.
a lot.
Mausumi also wants to share her views with us. May I request Dr. Mausumi?
Yeah, thank you very much, sir. First of all, I am really, it's more than a privilege to attend the sessions. The speakers, the eminent speakers which the team has brought, and the content, what they have delivered was more than awesome. I request the team to share those videos and the recordings, because what happens, we tend to forget. We get busy with our day-to-day schedule of teaching learning process, and we tend to forget what we learned. So it would be really helpful if you can share with us the recordings and the way the systematically how the entire program is organized. Every day reminder was sent, email as well as the SMS was sent. So I really appreciate all the effort. And last year also I attended one FDP. That FDP level was also very high, and this time it has exceeded even that level. So I am really grateful for the opportunity. Look forward to collaborate with the university and the eminent faculties, as well as to participate in the FDPs in the coming days. Thank you very much, sir.
Thank you, Dr. Mausumi. And our Dean, Dr. Parmanand, always believes in setting up new benchmarks every time. So we have to set up, we have to break our own benchmarks every time. So next time we will try to set new benchmarks for this FDP also. And as you said that the recordings, we will get all the recordings uploaded on YouTube, and the links will be shared with all the participants so that you can access them anytime you want, because they will be available on YouTube.
And even if any participants want to listen the past FDP also, they are also available on YouTube.
Now I think Dr. Al Hassan Umar, he also wants to share his views. Yeah.
Good afternoon, everyone. Today is really a wonderful day. We have really learned a lot from this program. I was opportune to attend so many programs of this nature, but this one has stand unique due to the nature of expertise and well-experienced presenters who has presented right from the beginning of this program. May I, at this point in time, congratulate all those participants who must have put a very nice effort to see the success of this program. I'm really educated. I have jotted down a lot from excellent participants, from excellent presenters in this wonderful program. Thank you very much, the team that stand to ensure the success of this program, and the management of this particular department and the faculty who has also provided a fertile ground for such kind of international program of this nature. Thank you very much. I really appreciate. I wish a successful success ahead. I remain Umar Al Hassan Ahmad. Thank you very much.
Thank you, Mr. Umar. Thank you so much for your kind words. Is there anybody else who wants to share his or her experience, or wants to give his or her feedback to us? I think we are done. Dr. Ankur, over to you, sir.
So as feedback, we will try to set new benchmark in our upcoming events, especially in our next RACSAD series, which will be coming. So we will be sharing that detail to you. Along with that, we want to make one more announcement here that we are going to organize one international conference from Springer, that is second in series. And that conference will be held on 29th and 30th October. For that, paper submission is still going on. So we will be sharing you the call for paper for that particular conference also. We will request you kindly submit your valuable submissions, your valuable manuscripts for that. And if you are free for reviewing some papers also, as we have requested you earlier, we will share you one link for that through which we will share the request to you on Easy Chair. So kindly accept that. With this, now again, thank you to you all and the team, and especially our Dean sir and our HOD sir. Thank you so much for being with us during the FDP. Thank you all. Gaurav sir, kindly share the feedback link so that the participants can submit their feedback. This meeting will remain open for next 5 minutes so that you can submit your feedback. After that, we will close this.
Ankur sir, I think Dean sir wants to say something.
Yes.
Dean sir, do you want to say something,
Please.
sir?
No, I'd like to thank you all participants. And as rightly said, every time we are setting our own benchmarks, that's a part of life, and achieving the greater and greater heights every time. We need to find the challenges and set the goals according to that. And we need to overcome those goals and challenges. Thank you. And once more, congratulations to all of you. Thank you. Thank you.
Thank you,
Thank
sir.
you, sir. Thank you so much for your kind words. And it's all because of you, sir. You have good faith in us. You always give us free hand to do whatever we want to do.
Well done.
Thank you, sir.